This is Physics 2, Chapter 26 in Relativity, and this will be Part 2. We left off right before getting into length contraction. And for this, we're going to look at this little example here. We have a spaceship going from Earth to Neptune. So in frame A, and if we look at the spaceship as what's moving, and it's moving away from the Earth. Spaceship has a certain velocity, Earth and Neptune are not. And so we have a distance between the Earth and Neptune, as we're going to say as LO, or L naught. And then the velocity, of course, is going to be V of the spaceship, which we're assuming here is going to be close to the speed of light. It doesn't have to be a speed of light, but it's going to be close to it. And so this distance, this time it takes is going to be just that distance divided by that speed. Now we're going to look at a different frame, and that is the astronaut is on the spaceship. They watch the Earth moving away at very high speed V, and Neptune coming to them at very high speed V. So as they see it, it looks like the planet's moving towards them at some very high speed. The time that astronaut experience is the proper time, since the arrival on the Neptune and departure from Earth both occur on the spaceship. Alright, so his time is going to be what's considered arrival. He experiences both when he leaves here and when he arrives on Neptune. And so we're going to start with that. So the time it takes to go from Earth to Neptune is equal to the time the astronaut experiences it to go, his time he experienced to go from Earth to Neptune, over this square root of 1 minus v squared over c squared. So now if we solve this for the proper time, and so you have the proper time equals the change in time times square root of 1 minus v squared over c squared. Alright, from frame A we have that time is that distance from Earth to Neptune over the velocity. So we have LO over V times square root of 1 minus v squared over c squared. We can multiply both sides by V. When you multiply both sides by V, this V cancels. Here you have V times the proper time, which is going to be the length. And that would be the length between these two, Earth and Neptune, at this point. Or the length that the person experiences that it travels. Think of it as the length of the odometer on the spaceship, assuming that they have an odometer. And that's going to be equal to the proper length times the square root of 1 minus v squared over c squared. Another way of writing is L is the proper length over that gamma. And so the length of an object moving relative to an observer is measured to be shorter along the direction of its motion than when it's at rest. Right? So it contracts. How much it contracts depends on the speed that the object is moving. Right, so we'll get into a couple of examples here. First, for a 520 meter long spaceship passes by Earth, we want to know what the length would the people on Earth say the spaceship was as it passes the Earth at 0.87 c of the speed of light. So length is equal to the proper length times the square root of 1 minus v squared over c squared. Right, the proper length here is going to be the actual length of the spaceship as it was created. So 520 meters times the square root of 1 minus, and then the speed is 0.87 c squared over c squared. And so when we put this, we get 520 square root 1 minus 0.87 squared. And you put this in a calculator and you end up with 256.4 meters. Okay, so it's shrank almost halfway. Actually, maybe a little bit more than halfway. All right, the next one, so this is 4, 5. A 25-meter long beam is shot past a stationary spaceship at 0.99 c. What length does the people on board the spaceship measure the beam to be? Right, so you have L equals L sub 0 times square root of 1 minus v squared over c squared. L sub 0 here is going to be the 25 meters long beam, and that beam is moving at 1 minus 0.99 c squared, and then c squared on the bottom. And we get 3.5. Okay, so we will see this as 3.5 since this what would be a longer object is moving that fast. We would see it as it looks a lot shorter. Alright, so the idea behind this deals with 4 dimensions where we have space and time. So instead of what we think about with 3 dimensions where we have x, y, and z, we're dealing with the 4th dimension where we have time involved as well. And the idea is if you have any change in one of these 3 being smaller, which would be a contraction, you get a longer time, which would be the time dilation. And so we see this kind of resemblance with things before. If something, for instance, if you squeeze a balloon, which is what's going to be here, so let me kind of draw the balloon. You press in here, your x-axis kind of decreases as you press in. Try and draw the balloon as best as I can. But the y-axis results in a change. This moves up. The same idea is working, but instead you have the change within the time as you have a change within all 3 of these dimensions that counter that change. And so this first part is that's experiment 1. Balloon is squeezed, resulting in horizontal being reduced, um, but you get an increase in your vertical dimensions. So in experiment 2, that balloon's in 4 dimensions. Because it's moving at a very high speed, you you get the diameter around the balloon contract from based on the observer. So you get this balloon, when it moves at high speed, becomes smaller in all dimensions. And because of that, you end up with the time increasing in length. Okay. So now, if time is going to change, anything that depends on time is kind of going to change too. So what depends on time? Well, let's start with momentum. Momentum is mass times velocity. Well, what's velocity? Velocity is your distance over time. So it's going to depend on time. And so you're also going to see energy change. Well, I'll get into energy, especially kinetic energy, here soon. We have, with both energy and momentum, we have what's called conservation of momentum. So because you get a change here, well, we need that change to be conserved. And so relativistic momentum is going to have that factor of gamma involved. So you have the mass times velocity over the square root of 1 minus v squared over c squared, which we write as gamma mv. This also means that we can see that there is a change in the mass in a sense. And so this, I'll write over here, gamma mv, this gamma m is what we're going to call the relative mass. Well, m itself is the rest mass, as I have on the paper over here. Alright, so let's do example 6. We want to know what the momentum of a 5 kilogram rock is traveling at 0.99 c. So 5 kilogram rock is your mass. So I'm going to find the relative mass first. That will be the mass over square root of 1 minus v squared over c squared. And I get 5 over 1 minus 0.99 c squared over c squared. And take the square root. So 1 minus 0.99 c. Well, the c's canceled out, so 1 minus 0.99 squared. Take the square root. And you get 5 divided by that answer, and you get 35.4. And this is going to be kilograms, since the mass was in kilograms. So that holds the unit. So your relative mass is going to be 35.4 kilograms. So now we can go as far as finding the momentum That's relative. And it's going to be gamma times the mass times velocity. So 35.4, which is these two, times the 0.99 c. So we get 35.046 c, which we can write, I'll multiply c out as 1.05 times 10 to the 10th. Alright, so we can do the same thing now with something traveling even faster. Alright, so I'm going to actually skip this step here. I'm just going to go right through the equation. So relative momentum is our rest mass, which is 5 kilograms, times the speed, which is 0.999 c, over square root of 1 minus 0.999 squared, c squared over c squared, so that cancels. Oops. And I get 3.35 times 10 to the 10th. This is be Newton seconds. Alright, so the ultimate speed, that is the speed of an object cannot equal or exceed the speed of light. So what if we assume that v equals the speed of light? Well, we get 1 over 1 minus v squared over c squared. That take the square root. When we do that, we end up with 1 minus c squared over c squared, which is 1. So you have 1 minus 1, which is 0. So you end up with 0 on the bottom. And we really can't divide by 0. Right? So this creates that limitation there. If x is greater than the speed of light, it becomes even worse because you get 1 minus x c squared. So this x is assuming that it's higher than 1, because that way it's higher than the speed of light. So you end up with 1 minus x squared. X is higher than 1, so you're going to end up with a negative number, and we can't take a square root of a negative number. Matter of fact, we'll have an imaginary number at that point. So this is where it creates that barrier for the speed of light. Alright, so now we did momentum. Now we're going to look at energy. So let me get new blank sheet, basically. And specifically, we're looking at kinetic energy. Since we know kinetic energy is equal to 1/2 mv squared traditionally. So it depends on v, which depends on time. And so the kinetic energy of an object that's traveling at a relativistic speed is going to be equal to this mc squared, or c squared is speed of light, over square root of 1 minus v squared over c squared, where v is the speed that it's traveling on at. And then we're going to subtract mc squared. Right, so this way it's gamma mc squared minus just mc squared. And we can look at it as, if we solve for this, gamma mc squared is equal to the kinetic energy plus mc squared here. This gamma mc squared is the total energy of the object. Mc squared is the rest energy of this object. So this is the rest energy, this is the kinetic energy, which is the energy of it moving, and then this is its total energy. So since we now know what the total energy is, we can write the energy total, which is equal to gamma mc squared, as mc squared over square root of 1 minus v squared over c squared, right, which is also equal to the kinetic energy plus the rest energy, which is mc squared. Okay, so if the kinetic energy is 0, we have E equals mc squared, which we now know is Einstein's famous equation. And so this applies to all forms of energy. Change in the energy requires a change in mass. So the sun radiates energy and is decreasing in mass because of it. Particles have been used to convert their mass completely to energy during collisions. And we see this in like a nuclear bomb. It takes the mass of particles and gets energy out of it, making an explosion. So we can think of this as a change in energy equaling a change in mass times speed of light squared. Right, so ideally, how much energy would be obtained from a 0.5 kilogram golf ball? Well, if we change all that mass into energy, so we have 0.5 times speed of light squared, that will give us 0.5 times 3 times 10 to the 8th squared times 0.5 gives me 4.5 times 10 to the 16th joules. That's how much energy that we can get from just a 0.5 kilogram golf ball. Right, so now if we look at, and let me see if I want to do some of this algebra. Let me start with what we have. So we had E equals mc squared over square root of 1 minus v squared over c squared. I'm squaring both sides here, so this side becomes e squared, this side becomes m squared over c to the 4th, that'd be c squared squared, and then I get rid of the square root here. Then what I do here is I break this up, and I break it up just so I can use pieces of it to get what I want. And so this is where I make it really confusing. I'm adding and subtracting v squared in order to get v squared into this numerator from one of these. So I have c squared minus v squared plus v squared, which this is just equals 0, so I'm not really doing anything to it. Just writing it in a unique, weird form. And so what I can do here, let's see, so I'm breaking this up into two pieces. So first I'm distributing this m squared c squared to this v squared, and that becomes this part. And I'm breaking up the denominator so it's two fractions instead of one, since these are the same denominators. And then I'm distributing the m squared c squared into this portion, but I'm not separating them. This mv squared becomes your momentum squared, along with this 1 minus v squared over c squared. Okay, so that's where this momentum comes, is this section here is your momentum squared. Right, so if we remember, momentum is mv over square root of 1 minus v squared over c squared. If I square momentum, d squared, this I get rid of. Right, and then here I factor out a c squared. So I brought out this c squared, which means I brought out one from here as well to make that c to the fourth. Right, so that's where it becomes momentum squared c squared plus m squared c to the fourth 1 minus v squared over c squared. And then this whole thing is 1 minus v squared over c squared. Right? And then I can divide this out. And so this is why I get m squared c to the fourth. And this now relates energy to momentum. And then we can use this. So we look at a photon. It has a certain speed. That speed is the speed of light. And so this requires the mass of the photon to be 0. The energy is equal to hf. And then our momentum, we're going to do it this way. We're going to look at that energy here. E squared equals p squared c squared plus m squared c to the fourth. Because m is 0, that part is eliminated. And so you have e squared equals p squared c squared. So we can take the square root of both sides and we get e equals pc, which is really nice. But then we get p equals e over c. Well, e is hf, so now we have hf over c. Well, f is c over the wavelength. So now we have hc over the wavelength over c. Those two c's cancel out, and you get h over the wavelength, which is Planck's constant. Or I'm sorry, not Planck's constant, but Planck's. Actually, no, it's not Planck's. It's de Broglie's equation. Right, so P equals h over lambda. So we use relativity to show an equation that we've shown before in multiple ways, which helps confirm that what we're doing is on the right track with things. the last thing we're going to look at is relative velocity. Let me check the time on this now. Okay, I can finish this. This one is maybe a little bit more confusing with things, with the way everything is, or it can be at times. So here we're going to consider speed of light being an absolute limit and cannot be exceeded. So we suppose object A is moving with velocity u prime, which is going to be relative to object B. And B is moving with a velocity v in the same direction relative to object C. So in this picture, C is Earth, B is this rocket, and that rocket is shooting another rocket, which is going to be A. This rocket has speed v, this rocket has speed u prime, which in this picture is point C of gravity, or not gravity, I don't know what I'm talking about that, point C is the speed of light. And then u would be the speed that this rocket is relative to Earth, right? So this is the speed relative to this. This is the speed relative to Earth. And then u would be the speed of this, I guess you should say, missile from the rocket relative to Earth. And so to find u, it would be the speed of the rocket plus the speed of its missile all over 1 plus the speed of the rocket times the speed of the missile over c squared. And then if B is moving relative to V relative to C, and A is moving with velocity u relative to C, then the velocity of A relative to B is given by u equals V minus u prime over 1 minus V u prime over c squared. So let me kind of work this out on the board of what I mean there in terms of picture. So B is moving at V. This is relative to C. And A is moving with velocity u relative to C. Right, so A is moving with velocity u relative to C. So think of it as the Earth, horrible Earth looking, but oh well, and two rockets are shot out. This one's B and this one's A. This one has speed v, this one has speed u. And we want to find the speed relative from A to B or B to A. Right? And so that's how this is different from this picture. This is going to be comparing these two speeds, and so you're going to subtract them to find the difference. This is kind of, this missile has a speed that's from this rocket, but that rocket has a speed from the Earth, so this missile is adding on from that speed, which adds on from that, the speed from the Earth. So that's why these are different, and how you can look at them. Alright, so if we want to find the speed of rocket 2 from this picture, okay, that's going to be using this top equation. So 9 u equals v plus u prime over 1 plus v u prime over c squared. So v was 0.6 c plus 0.6 c for the missile. And if we added these together, we actually be over c, will be 1.2 c, which would be a problem. But we also have this bottom part, which is going to be 0.6 times 0.6 over c squared. So this is 1.2 c over 1 plus 0.6 squared over c squared. And I'm going to leave this c here. So when I'm calculating, I'm going to calculate everything here. So now the c on that side. So 0.6 squared divided by 3 times 10 to the 8th, divided by 3 times 10 to the 8th again. Oh shoot, let me do it again. Alright, 0.6 squared divided by that, plus 1. Oh, I totally forgot something. There's two c's here. One there, and then I'll just make the c squared. One there. These are 0.6 c. Alright, so that's going to cancel out. I thought something threw it off. Alright, so let me do that again. 1 plus 0.6 squared. And so we have 1.2 over 1.36. And so this becomes, which you can see is going to be less than 1, 0.88 c. Okay, so this second rocket still doesn't go faster than the speed of light even when you shoot it from something that's already moving. Alright, so in this next example, we have an observer on Earth sees an alien spaceship approaching at C, 60% of C. The Enterprise comes to the rescue, overtaking the spaceship at 0.9 C relative to the alien spaceship. How fast will observers on Earth measure the Enterprise to be traveling at? So both the Enterprise is being measured from Earth and the alien spaceship is also being measured from Earth. So you have Earth, alien spaceship, and then you have the Enterprise. I'm not going to draw the Enterprise exactly. Something, I don't know. Worst Enterprise ever, but so Enterprise, alien, 0.6 C, 0.9 C, both are being measured from Earth. And so we are looking at U equals V plus, minus V minus, let me make sure I have U prime over 1 minus VU prime over C squared. Okay. So now what do we have here? Well, U prime is going to be what we actually want to solve for. Actually, I'm sorry. No. Let me look at this. Hold on a second. Yeah. Okay. So u is the velocity a relative to b. So we alright, so this 0.9, I'm sorry, I totally looked at this differently. That's what threw me off. This helps if I read. This was relative to the alien spaceship. So we want to know this one, what this Enterprise is from the Earth. Okay, so yeah, I could have just turned that into plus signs. So we'll start with this equation. Right. V is the velocity of the alien spaceship, and u prime is the velocity of the Enterprise. So we got 0.6 c, 0.9 c over c squared. And so we get 1.5 c over 1 plus 0.6 times 0.9. And we end up with 1.5 over 1.54 c, which equals 0.97 c. Okay. So really close to the speed of light, but still not past it. Right, the last one in this. So you are showing this figure. You have captain of spaceship A observes the spaceship E escaping with a relative velocity of 0.35. A missile M is fired from ship A directly towards ship E with a relative velocity of 0.76 c. Two relative to ship A. So both these two are measured from the ship A. We want to know, what does the captain of ship E measure the velocity of the missile M to be? So we want to know, what velocity is this missile compared to this ship, or relative to that ship. Right, so this is where we'll use U equals V minus V prime over 1 minus V U prime over C squared. This is the speed of missile relative to ship E. Okay, which is what we want to know. Best thing here, I mean, V and U could be anything, either one to a point, but it's probably best to make V the higher number so we don't have to deal with the negative sign. The actual numbers though coming out are not going to be much different. Since, these you're just finding the difference, or either be positive or negative, but it'd be the same number, and this is just going to be multiplying. And so you end up with 0.41 on top, C, and 0.734, which is 0.558 C. Alright, so that ends the chapter on relativity. At this point, we'll be getting into nuclear energy, which I think would be a lot less confusing to a point. There is a lot of stuff involved in it, but this stuff, it can be harder to grasp in a sense, or get your mind around, than nuclear stuff. Alright, I'll see you in the next video.